If you recall that in part 1 we did the general stuff and then we looked at line integrals, basic types. We looked at parametrized curve and we did 4 examples. In part 2 we're going to look at surface integrals and volume integrals. Now let's look at the surface integrals. And what are the basic types of the surface integrals? Well, you'll notice there are 4, whereas in the help page they list 3. This is the one that's not listed in the help page. Let's find out what these are. Scalar. The integration is against a vector, so the result is this vector of integrals. It is not the surface integral of a scalar. See that? Not heavily emphasized. I don't know what this is. This is the surface integral of a scalar over a surface. This f dot ds turns out to be flux. It's the integral of the normal component over the surface. And this cross product, well, this is the vector of integrals that you obtain. I never met this before. Now let's look at some details. The ds vector is the vector RU cross RV. So R is a position vector. This is the partial with respect to one of the parameters on the surface, because this is how the surface is defined in Cartesian coordinates. And this is the partial with respect to the other surface parameter. This cross product is the normal vector, because these are 2 tangent vectors. Cross them, you get a vector orthogonal, so it's normal. It is not a unit vector. Keep that in mind. This lowercase n is not a unit vector. Now, here, nx is the x component of this vector, ny is the y component, nz is the z component. And we come down here and we take the norm of ds vector. It's the norm of this vector. That norm in Cartesian coordinates, if the surface is given explicitly, is the square root of 1 plus zx, z sub x, right? Partial derivative squared plus z sub y squared. And dA is either du dv or dv du, depending on how you orient your vectors. So this integral is the scalar integral of f over the surface. So in other words, if f is 1, you get the surface area. F dot ds. Okay, now let's think about that. Let's take a unit vector. F dot the unit vector is the component of f against the normal, or along the normal. So this is the normal component of f. And d sigma is this square root, but this square root is the norm of n. So they cancel. So you end up with f dot n, where this n is not necessarily a unit vector, dA, which is either du dv or dv du, depending on how you set up your iterated integral. And this speaks for itself. This is the vector f with components fgh, nx, ny, nz. That's from here. You take that cross product, you get this vector of integrals. Now, corresponding to the parametrized curve command, there is this parametrized surface command, and we should take a look at a few examples. Suppose you have an explicit surface, z equals x squared plus 3y squared, and you can indicate parameter names. So you say parameters equals xy. Now it comes back and it says, okay, x is x, y is y. It's a little bit confusing, but you have to interpret it correctly. And z is z, x squared plus 3y squared. And the parameters are x, y. Now let's see how smart this command is, and let's give it, instead of this explicit surface, we'll give it an implicit one. And we'll say the parameters are to be x and y. But the parameters turn out to be z and y. And x has to be solved for in terms of z and y. Okay, let's not say what the parameters are. Let's see what Maple does. It names the parameters t1 and t2, which is really not easy to read. But it picks z as one parameter and y as the other. It forces you to pick x as this function. Well, let's see what happens if we say, all right, let's use parameter names u and v. Well, it follows the same pattern. Y and z are chosen as the parameters, and you solve for x. Let's take a plane. Let Maple choose the parameter names. So x is a function of t1 and t2. See, the parameters are y and z, t1 and t2. Let's see what happens if we say a plane with parameters x and y. Well, again, z is really one of the parameters. It's u. Okay, and this x is the variable x, and this x is the parameter x. Very confusing. Plane parameters, let's pick the names u and v. Y is u and z is v. Okay? If you give it a sphere, Maple recognizes that and switches to spherical coordinates. But if that's an elliptic or ellipsoid, and you say, I want to use the parameters u and v, well, y is u, z is v, and x is the square root. So nothing fancy. You've got plus square root and a minus square root. If you take that same ellipsoid and you say, all right, I want the parameters to be x and y. Well, now x is x and y is y, and z is parametrized. That kind of looks like this up here. So you need to invoke parametrized surface to see how Maple is describing the surface, but you have to pay attention to what the returns are. Well, for these next examples of surface integrations, I reinitialized. So there's a restart, bringing the physics vectors package, the aliases. Notice I'm only aliasing here. VectorCalculus. Here is a vector that we'll use. Here is a scalar we'll use. This is the VectorCalculus version of the vector field that this vector represents. Here is an explicit surface in this form, z equals, I call it S. The right-hand side, which is essentially z, I give it the name z. When I set z equal to 0, and if I solve for x, I get this square root, where it's plus or minus, but if I call it x, I can always write minus x. And if I solve for y, I get this expression, and I can, again, do plus or minus. Now, I'm looking at an ellipse in the z equals 0 plane, and so the major and minor axes are these numbers here, and I've called those numbers a and b. So again, let's do some examples. I have 4 examples. So the 5th example here, contains two parts, scalar against vector, scalar with scalar. If f is 1, this integral should be the surface area, not this one. And I'm taking as my surface z equals z, from z equals 0 up. To evaluate this first integral, we begin by saying parameterize surface S. And remember what S is. S is the equation little z equals big Z. And we have declared the parameters to be u and v, and Maple says, okay, x is u, y is v, and z is 10 minus 2u squared minus 3v squared. That's okay. I like that. Then we do the int equals int trick. 1 here for the function. The ds, the arrow over the top, that's s underscore. Surface equals s. In other words, this is the equation. Little z equals big Z. Surface equals s. Parameters equals. And here's where you put the bounds on for the integral. X is minus x to x. Y is minus b to b. I'm integrating first with respect to x, then with respect to y. The return is a vector. All right, this guy is a vector because the k hat. If you put in inert, you can see the iterated double integral. Here are the bounds, minus x to x, minus b to b. This is the surface normal. And where did that come from? How do you get that? Look at z. Surface normal for an explicitly given surface minus zx. So you're going to get, there's a minus sign already, so you're going to get plus 4x minus zy. That's where you get 6y and 1. That's what this is. So this is the surface normal. Let's see if we can verify this result. And we'll use the student vector calculus package. Now remember, int maps across vectors immediately. So this is the normal vector. Int will map across that immediately. X is minus x to x, y is minus b to b. The components are 0, 0, and this is root 6, root 5. And root 5 times root 5 is 5. There's your root 6. Divide by 3, pi. This is a vector. This is the way a vector looks in vector calculus. You could also use this syntax. This is the vector. So you're going to map onto the vector. xy equals region. Now you'll notice that here I'm integrating minus y to y, but up here I integrated minus x to x. This produced a dx dy integral. This is a dx dy integral. X, y. This produces a dy dx integral because this is the order controller making the appropriate inputs here to the region. You get the same answer. So these are the things that you would have to keep in mind and know if you wanted to work in this package or this package. Now this second integral is the one that should give us surface area when f is 1. So int, I use capital I here, 1, you put norm of ds underscore. When you were doing this integral, you used s underscore. Now here you use norm ds underscore equals, S stands for the surface. That's the equation, little z equals big Z. Parameters, this is where you put the bounds of the integrals. I put inert here so you can see what Maple is working with. I put inert here so you could actually see the integral. You can see the bounds on the iterated integrals. It's a dx dy integral. This is the d sigma. And then I evaluated this in floating point, and I got this number. And this is what you get if you were to evaluate this integral exactly. You have elliptic k, elliptic e, and elliptic pi. That's why I decided to float it. There's an alternative usage that we can take a look at here. Unit normal. So here is the normal divided by its length, unit normal, uppercase n. So function is 1 times n, so I'm integrating a vector. This is a vector. Remember s underscore, that's the vector version of the integration element. Surface, s is the equation, little z equals big Z. Parameters the same as above. The echo here with inert and big I. The echo here shows you a dot product between these two vectors. This is what Maple is going to construct. Here I use little I with inert so I can actually see the integral. It's the same integral that we got up here. It's dx dy integral, and it will float to the same number, 86, what have you. By way of verification, let's take a look at this VectorCalculus command, surface int. 1 is the function. Because it's a scalar, you put the variables. Surface is generic. You give the surface parametrically as the components of a vector, x, y, z of x and y. Now, that portion of the surface that is supported by the ellipse in the xy plane, you can tell Maple that there are a number of alternatives here. You can have triangles, rectangles, and what have you. Okay, x, y, those are the variables that determine this ellipse. You just give the equation of the ellipse, no solving for x or y. And I did it simplified because the initial return has tangents and arctangents, and this is much more compact. But you can get a hint here that Maple parametrized with some form of polarity, or it's using an angle, dx dy integral. And if I hit this thing with an eval f, do the unevaluated integral, eval f, and I get the same number that I had up here. Here's another way to access the surface int command. It's a syntax-free way, and it makes use of a task template. Where are the task templates? Tools, tasks, browse, tasks, calculus vector, integration, surface integration, and you can integrate, the surface could be a box, parametrically defined sphere. It could be defined over an arbitrary 2D region, or specifically over a disk, or over a rectangle, or over a triangle, or over an ellipse. These are surface regions known to the command. This is a syntax-free access to the command. We're integrating 1 because we want surface area. The surface is z equals uppercase Z. Here's the equation of the ellipse. We can integrate over the full ellipse or over a sector of the ellipse. Click, you get the integral value, you get the floating point value. And take a look at the command itself, a couple of versions of the command itself. One, it's a scalar, so you've got to name the variables x, y, z. Over a surface, you define the surface parametrically, x, y, z of x and y. If you put y, then x, so no use of the ellipse, the known ellipse equation, y, x, you get a dx dy integral. Y being first means it's the outer integral. It's the first bounds out here. Depends on how you write your integrals. I always start with the inner one. So that to me is the first one. Okay, then if it's xy, then it's a dy dx integral. So there's some flexibility here with the surface int command. Here's yet another way to access that same functionality. You can see the path to the test template. It's surface integral on a surface defined parametrically, so we get a more primitive. Functions 1, x is x, y is y, z is z of x and y. When you make appropriate substitutions into this function, we'll call that capital F of uv because it's a different function than little f. The length of the normal. Okay, so that's going to give you the d sigma. You pick your order of integration, du, dv, dv, du. You put the appropriate bounds working closer to first principles. Here you get the dx dy integral, having chosen the essentially dx dy, and this is the floating point value. And yet here is one additional integration tool for syntax-free computing. This is a more visual double integral command. You pick your area element dx dy, dy dx. This shows you the template. Psi is the d sigma, without the dx dy, it's d sigma. You put the bounds, the appropriate bounds according to your choice you made here. You get these two graphs, graphs. This is the region in the xy plane, and this arrow tells you you're integrating in the y direction first. See, it's a dy integral, and this, it's not a volume, but it's what you're integrating. This the stuff you're computing by this integral. So I put the quotes around volume. So it's just one more visual tool for seeing what the double integrals involve. So in example 6, we begin with the same two integrals that we looked at in example 5, only we have made the function f to be this, x squared y squared z, rather than 1. The evaluation of this first integral, int f, where f is this, surface, so this is the vector form ds, vector, so you just write s underscore, surface, this is z equals z, parameters, this is where you specify the bounds of integration. You can see that we have an answer here, and it is a vector. If you put in inert, you can see the dx dy integral, the iterated double integral that this sets up. This, if evaluated, gives that. We can verify this using the VectorCalculus package, mapping int of this function. Okay, so here is the x squared y squared z. You've got to evaluate that on the surface, what z is, and that's being multiplied against this normal a derivative of the normal vector. So that's the differential. And you give it the bounds, and you get the same quantity expressed as a vector in column vector notation, third component, third component. So here is the evaluation of the second integral. This is the one that's actually a surface integral of f over the surface. Unit normal. All right, minus Cx minus Cy, 1 divided by its length, unit normal. So here I've opted to do it with a more basic approach. So here is f. Here is the unit normal. So normal vector, vector. So here we just write s underscore. We don't say norm. Surface is little z equals big Z. Parameters, that's where you put the nitty gritty of the bounds of integration. And you can see here this vector dot this vector. And this vector contains this square root, and they cancel out. So when you ask for the inert form with little I, you actually see the integral. It's kind of messy, this integral. And so here I've just wrapped it with an eval f, so that maybe we'll do a numeric integration and you get this value 170.95. Of course, we would like to verify this, so let's make use of the surface int command in the student vector calculus package. So surface int, this is the function f, x squared y squared z. It's a scalar, so you have to put the variables here. Surface, given parametrically, x, y, z of x and y. It's over an ellipse. Let's make use of that facility. xy equals ellipse. The easiest way to define the ellipse is to say z equals 0. That gives you 10 minus 2x squared minus 3y squared. And let's just see what that integral looks like. Now I wrapped it in simplify because the first output has arctangents and tangents, and this is a little bit more compact. And then I hit that with an eval f. This just recreates the unevaluated integral. Hit it with an eval f, and we get the same 170 that we got here. We've seen this tool before. It's a test template. Surface integral on a surface defined over an ellipse. Here's the function f. Here is the surface z. It's over an ellipse. We can write the ellipse as z equals 0. Full ellipse, the integral. You see Maple uses polar coordinates. They are d theta. Here is the integral. Here is its floating point value. Just another tool in the existing Maple arsenal. Here's a look at the use of the surface int command in a more primitive mode without making use of the ellipse option. The difference here is that you must indicate the bounds of integration in this order, y, x. That makes a dx dy integral. Whoever wrote this command took first to mean the outer integral. And if we hit that with an eval f, we get the 170, etc., that we expected matches this 170 up here. In example 7, we evaluate the integral f dot ds. This is a vector. This is a vector. This will be the vector f, same surface, s. This is the one that turns out to be flux, okay, because there is a normal hiding in here. F dot n, the normal, that's the normal component, so you're actually computing flux. to evaluate this using the tools of the physics vectors package. First, I've done int with a little I, f is a vector, ds is a vector, so you write s underscore. Surface is s, that's the equation, little z equals big Z. And in parameters, it's where you put the bounds for the integral. Inert, this gives us a chance to see what the inert integral looks like. It's a dx dy integral. If you do this int equals int trick with no inert, then the little int here evaluates the integral, and this is what you get. Now, notice that this root 30 is root 5 root 6. So there's a root 5 times a root 5. So there's a 5 times a 5. You could write this as 25 over 3 pi root 6. Now, I'm going to verify this in each of two ways. First, I'm going to use the flux command in the student vector calculus package, because this is, after all, is a flux. This is the vector calculus version of the vector field corresponding to this vector here, f. The surface is defined x, y, z of x and y, and you notice because vector fields carry their coordinates, we don't have to put anything in front of this surface. And I'm defining it over the surface over an ellipse. So this flux command knows these same regions. Easiest way to define the ellipse is to say z equals 0. And here you get 25 root 6 pi over 3, whereas here we had to do that mentally. Now, the second way to verify that is get back to first principles. Unit normal. There's normal and its length. Let's dot g with n. So this is the normal component of the vector field. And here we are evaluating it on the surface. And I put that into the surface int command. It's now a scalar. So I have to put x, y, z here in the surface. I define the surface x, y, z of x and y. It's defined parametrically over an ellipse. Define the ellipse z equals 0. That will give us the ellipse. This command, surface int, puts the sigma for us, takes care of that, which essentially cancels out this square root down here, and we get the same number here as we got here. In example 8, we're doing the vector integral that has a cross product, vector, vector, cross product. Here is the vector, same surface that we've been using. This vector is chosen so that I don't get a 0 result. I don't want a 0 result because then I don't know if I've made a mistake or what. I want a vector where the integration result is doable, non-trivial, but doable and not 0. By way of solution or evaluation of this integral, here's the vector. Define it because it's different from previous. I make use of little int. Here's the vector. Since ds has a vector over it, I write s underscore. Surface equals s. Maple knows what that s is. Little z equals big Z. The parameters is the nitty gritty, where you have to put the bounds of integration. Kind equals cross product. And I've put in inert so I can see something. And I've done a collect on ij and k so I could more easily compare this to a result I'll get using some of the older tools in Maple. And collect takes simplify, and I'm mapping this collect onto the components of this integral. If I do the int equals int trick, all of this stuff is the same. Kind equals cross product, no inerts, no simplifies. And you see you get the value. It's a vector, 500 root 6 pi over 9, because of that k, it's a vector. Of course, we want to verify this as much as we can. So here's G as a vector field in the VectorCalculus package. N is a vector field in the VectorCalculus package. It is not a unit vector. I take the cross product between G and N, and I evaluate it on the surface. This gives me a vector Q. Since int maps across vector automatically, all I need to do is define the appropriate region of integration in the xy plane. So I'm integrating Q over that region for each of the components, and I get 0, 0, and that number is the same number I get here. The K tells me it's a third component. Down in this section, I clarify for anyone who doesn't see it that the vector normal, if it's a unit vector, it's n over n, but d sigma has that same norm of n in it, and these two things cancel, and so you end up with f cross little n, which is not necessarily a unit vector. And that could be puzzling as to whether or not you need a unit vector or not. But you don't, because of the way d sigma contains that same norm of n. And here I've used the surface integral command. Here I just used int to map across. Here I take a cross product with G and the vector field. Now this is the unit normal, evaluated on the surface. Surface is given parametrically x, y, z of x and y, and I'm doing it over an ellipse. And that version of int maps across the vector, and you get the same vector here as we got here. Now we take a look at volume integrals. There are two basic types of volume integrals. F dv, iterated triple integral. The dv is defined as the box product. So this is a cross product here dotted with this vector here. It's the volume element. In Cartesian coordinates, it's dx, dy, dz. Okay, so this is what you would be integrating on the left side of the divergence theorem. Volume integral of the scalar f is equal to the flux through the bounding surface. This is an integral that I've not seen before. The result is a vector, because this f is a vector, but dv is a scalar. Right? Box product is a scalar. And so it's a vector of triple integrals. So just as there was a parametrized curve and parametrized surface command, there was a parametrized volume command. And what's illustrated in the help page is application to a sphere. And Maple recognizes that and immediately switches to spherical coordinates. So I said, okay, what if this was an ellipsoid, not a perfect sphere? And it didn't work. I got back these error messages of the order that this doesn't work. And there's no, to my mind, there's no difference between these two. This worked, this didn't. This Maple will switch over to spherical coordinates, and this it didn't handle. It took me a very long time to get to this point where you describe the surface. X is u, y is v, z is w, and the parameterization is x of uvw is u, y of uvw is v, z of uvw is w. That was a revelation that took a long time to become clear. So in order to do some examples, we reinitialized as follows: the physics vectors package, a couple of aliases, VectorCalculus, MultivariateCalculus. If I'm in VectorCalculus, I want my vectors to be column vectors, a vector, a scalar, the VectorCalculus equivalent of the vector field ABC, the surface bounds on the projected ellipse, semi-major, semi-minor axes of the ellipse. Here are some examples. I have two examples. Example 9, I'm going to evaluate the integral of a scalar over the volume element dv. So this is the integral that you would expect to see on the left-hand side of the divergence theorem. To evaluate this integral using the tools of the physics vectors package, big int, little int. But look at what you put in here. This is the scalar f, the letter v, not dv, not v underscore, the letter v. Then you write the word volume, and look at what you put for the volume. What you got when you did parameterized volume to work. X is u, y is v, z is w. In the parameters list, you put the details. The range for z, the range for x, the range for y. Notice the order. Z, x, y. And the integral that little int inert provides is a dz dx dy. So zxy, zxy. And if you take away the inert, this is the value of that integral. There's a caution that I would like to provide, and that's right here. And it was a result of some experimenting I did. The integrand to be 1 dv dx dy dz, right? V. Volume parameters. Okay. Z first. X second. Y third. So you get dz dx dy integral. Makes sense. Then I said, how about if I wanted to go dz dy dx? So I interchanged these two ranges. And lo and behold, I got a dz dy dx integral, but a minus sign. So there's some kind of cyclic permutation stuff going on in here with the volume element that I don't understand. But it's a caution. Be careful. For the time being, I think you got to live with dz dx dy. Now, of course, I'd like to verify this result. So int, notice the colon dash in front, so that this becomes the top level int, because int up here in the package, in the physics package, is bound to this new version of integration. So this gives me the top level version. Here's the integrand, list of ranges as equations, z, x, y. So that gives me a dz dx dy integral. And the value of that integral is the same as we have here. There is another way to tackle this integral. Use the multi-int command from the MultivariateCalculus package. Multi-int function ranges z, x, y. And here I output the integral, so you can see you got a dz, dx, dy integral. Its value is the appropriate number. You could say yxz, which controls the order of integration. You get dz, dx, dy, so it is backwards, z, x, y. Region, you give these ranges, not as equations, but as ranges, you get the same integral. And you can access this multi-int command from the context panel in a syntax-free way. So you load this package, you bring up the context panel on the scalar f. There's a dialog that you pick here. There's a drop down. You specify the coordinate system, Cartesian 3D, and these three options are the axes, and you put x, y, z. Then when you say OK, you get the second dialog, and here's where you pick the order of integration. dz, dx, dy. You put the z range, the x range, the y range. Here I've picked output equals integral. This is the integral that you will see. It's a dz, dx, dy integral, and it's this one. For our final example, example 10, we want to evaluate the integral of vector dv. So f is this vector, v denotes a region bounded by this dome, and the planes equals 0. Let's evaluate this integral using the tools from physics package. So we write capital I here for int and an inert over here so we can see what the output looks like. Vector here, the letter V here, the word volume, and then x, y, z equal u, v, w. The parameters is where you put the bounds of integration. Z, x, y. Inert here enables you to see what the integral is going to look like. Small I with inert, you actually see the integral, so you get a dz, dx, dy integral. The integrand is the vector f. If you remove that inert, then you get the value of that integral, which is a vector. And you can see the components a, b, c, they're all multiplied by the same amount. There's a caution here that I'd like to call your attention to. It's something that we've already just seen. You set up the integral. If you change the order of these ranges, z, y, x, rather than z, x, y, notice the minus signs? So again, you negate the integral by inverting these two ranges. Some kind of cyclic permutation is going on. Finally, I'd like to verify this result using the int command in VectorCalculus package. That's a command that maps automatically onto vectors in that package. There's the vector G, the vector field version of vector F from the physics package. This ordering defines the order of the differentials. These ranges correspond. This gives you a dz, dx, dy integral. Its value is the same vector that we got from the physics version of int.